Okay, hello people. Happy
Hello.
Thursday. It's almost Friday. Hooray. Okay, so for attendance today, please go to the chat and tell me, what tattoo do you have? Or if you don't have a tattoo, what would it be if you got one? If you ever got a tattoo, what would it be? Or what do you already have? If you have several, just pick one. So this is how we will do attendance today. Okay, thank you people for your tattoo information and for completing attendance. I have a few kind of just updatey things first before we get back to the science. We do have a group me for the As You Learn, for this class on the As You Learn page. You will find the link to join that. And I've just added Dr. Chandra on there. So this is I know y'all maybe have a separate one for just students, which I think is great. But this one is with the professors so that you can quickly ask us questions, which might be science questions, or they might be like, when is this due? It says Tuesday here and Thursday there. So if you're just trying to figure out what's going on, that's also a nice way to communicate. And you can also communicate one-on-one if you want with me or Dr. Chandra on there. So anyway, a way to communicate. There's one. All right, another thing I wanted to update you on was just the As You Learn page in general. I have included this line kind of thing to separate assignments on the bottom from kind of information or references or lecture information or videos on the top for each week. So for this week, we don't have any assignments due, so there's no assignments listed. For next week, we do have some assignments due and then some like other, the assignments are down here and the lecture stuff is up here or information. Okay, and also take note of these images in each section. They do have meaning. So they're not completely random. That was the lamest one. Anybody know what this one is? What's this image? And why would I put it in week 1? Here, I'll zoom in. Maybe you people can see it better.
Isn't that the Dr. Hester? Isn't that the rover that crashed into Mars? The one that they lost like $1.5 billion on?
It is. That's the one. It's called the Mars Climate Orbiter. And this is an artist's rendition of that instrument. And yeah, it did crash into Mars. And we lost millions of dollars, we being the taxpayers. So does anybody remember why it crashed?
One team used metric and the other used imperial, and they didn't list their units on their measurements and engineering stuff. So they mixed those up.
Oops. Yeah. It was actually more deeply embedded. It was like somebody was using a software, and the software, it wasn't clear what the units were in the software or something. So yeah, it's pretty much what you said, but yeah, oops. So units were neglected and millions of dollars were lost. So since we were talking some about units last week. That was the image that I put up there. And so the one for this week, whatever, upcoming images should also help you kind of like easily scroll to a section of the As You Learn page if you want. But they are also demonstrative of what we are learning that week. So this is our linear least squares regression week. And this is showing basically the essence of linear least squares regression in that image there. We'll talk about that later. Questions about the As You Learn page? Okay, we have a couple of homework assignments coming up due next week that I didn't actually state out loud yet. We have homework 0.5. I want you to basically get started on Python, like get it loaded on your computer and make a graph with data I gave you. It should not be hard. You should just be following the instructions from the Jupyter Notebooks and Python for Data Analysis PDF, and then the Jupyter Notebooks and Python PDF. Those PDFs there tell you what to do. Okay, so you're gonna upload a PDF here of your graph that you make with Python. Okay, so that really shouldn't take very long. I think Sam already did it. How long did that take you, Sam? Danae?
It took me maybe like half an hour, and I've never coded before.
Okay, so
Only an hour.
yeah, it should take everybody about a half hour. And then we have homework 1 that is due on the 4th. So that is a week from today. And that's covering the stuff that we talked about last week, some of the stuff we talked about this week in lecture. So that's from your book, Taylor, your textbook, which is also linked at the very bottom of the As You Learn page. You scroll all the way down, there's a PDF here of that book. Okay, and there's also a Python Programming for Computations book. If you want to go a little deeper and like start playing with Python, there's a reference for you. But there's a lot out there besides this. Okay, questions about homeworks? Everything is submitted on As You Learn in PDF format by 4 p.m. on the due date. Why Python, you ask? Well, I know you're learning Origin in the lab section of the class. So we are exposing you to 2 different software, Origin being the plotting software that you're learning in lab. So Python is a software package that can also achieve plotting, but then you can do a lot more with Python. It's free, so that's really nice. And it's very powerful. It can make really nice graphs. It can also, you can write code to do computations, like calculate things. Can't really do that in Origin. Origin is just for plotting, but it does a really good job of plotting as well. So you'll be learning both, and both will be useful for you beyond this class. Okay, another thing that I'm realizing is that it was taking me way too long to put y'all in those breakout rooms. Holy crap. So I'm just gonna open breakout rooms, and I'm gonna show the list of what breakout room you go to, and then you just go to it. And that should be a lot faster. I'll show this list whenever I tell you to go to your breakout rooms, because it was taking me way too long. We don't want to waste time. This is precious time we have together. All right, and then once you're in that breakout room, you'll be with your team, and you should, figure out the answers to the questions I've asked you. And please choose one person from your group to be like the representative to give your answer back to the class. And that person needs to write their answer on a piece of paper kind of big and hold it up so we can see it. I have trouble like hearing math. I'm not sure if what you said, Ethan, was correct or not. I have no idea last time, because it was like I was just listening to your answer. So That one person needs to write down their answer so we can see it, unless it's a word like uncertainty, that's fine. I'm talking about math, like if your answer is a numerical value. Questions? Okay. So last time we stopped with some questions that I asked you all, some breakout room questions. I want to go through the answers for those, and then we'll move on to finally getting to this discussion of deciding uncertainties on particular devices. Okay, so here we go. This was the question that was asked of you all in your breakout rooms last time. So this was the first one that I asked you. This number was given to you, 1.45392 plus or minus 0.14389 grams. And the question was, how should that be reported? So I'm going to walk you through it. We should take that uncertainty, wherever that came from. It's like the weirdest uncertainty I've ever seen. Whatever. We know it has to be 1 sig fig. So we take this and we round up to 0.2. We always round the uncertainty up to be safe and to be the most honest. Unless it was like 0.10001, and that's ridiculous, so we would round down in that case. So we have to kind of decide what's best. So there it is, there's our plus or minus 0.2. We also take our value, our measured value, and we have to make its precision match the uncertainty. So the last digit is in the 10th place for the uncertainty, so the last digit for the value also has to be in the 10th place. So we take this 4, 5, we round up to 5. Our final quantity here is 1.5 plus or minus 0.2 grams. Is that how we should report it though? What are the SI units for mass?
Kilograms.
Kilograms. Thank you. Yes. So I converted this to kilograms. It's not really a rule, you know, but we really do want to stick to kilograms unless there's some reason not to. Like in medical physics, sometimes we use grams because that's just what people use in certain like medical physics labs or medical labs. But in this class, we're talking about pure physics, basically, pure metrology. So we're going to try to stick to SI units. So the final reported value for this should be 0.015 kilograms plus or minus 0.002 kilograms. Any questions about that?
Shouldn't the uncertainty have another 0 before the 2? When you converted from grams to kilograms?
Oh. Does it? Maybe I converted wrong. I'll check that. I think you might be right. I might have been off by a decimal here for both of these values, but I'll check. Okay, other questions? All right, let's do the next one. Number 2, so this value was given 1.45392 times 10 to the 15th plus or minus 843 times 10 to the 12th meters. So that's just weird. We have different times 10 to the whatever, which is not helpful for really understanding how much is that uncertainty compared to that value. So what I did was first line up the times 10 to the quantity for both values so that they matched. So I left the 1.45392 times 10 to 15 alone, and I converted this to 0.843 times 10 to the 15 meters. So now I can see how my quantities compare to each other easily. I just need to look at the value before the times 10 to the 15 to really know how much those compare. So I know I need to convert my uncertainty to 1 sig fig. I round up to 0.9 times 10 to the 15 meters, which means my precision over here has to match. So I round up my 4.5 to 5. So I have 1.5 times 10 to the 15 plus or minus 0.9 times 10 to the 15. And then I put those quantities together in the parentheses to minimize the text and reading, the amount of reading somebody has to do. Any questions about that one? Is this what y'all were getting when you were in your groups? Okay. All right. Now we have number 3. This was just a number and no uncertainty was given here for this one. 1.4569 meters, that was it. Somebody just gave us that measurement and no uncertainty. So we have to imply some kind of uncertainty since we know this is a measured quantity. So we take this place, this most precise place, and we assume the uncertainty is half in the digit of highest precision. So I think I wasn't saying in the digit of highest precision. I was saying half. I don't know what I was saying, but we take 1/2 of this tenths place basically and assume that to be the uncertainty for this number. So we end up with plus or minus 0.0005 meters so that the precision of our measured value matches the precision of our uncertainty. And we've kind of gone to the middle of the road. It might be 0.1, you know, as the real uncertainty. It might be 0.9 as the real uncertainty. So we're taking an average of like randomness and guessing in the middle, 0.5. So you can think of that as a value of 1/2 in the least count spot, or in the digit of highest precision, in the location of highest precision. Questions, comments? Okay. This is already posted on the As You Learn page, by the way, for all of you taking notes. Sorry, I should have told you that earlier. Okay. This is really similar. It's just got a times 10 to the minus 15 on it compared to the last one. So it's the same process as the one we just did. We basically take the same answer and tack on a times 10 to the minus 15 meters there. It's the same exact idea. Okay. It does look curious, this very highly precise measurement, I would have to say. I would doubt they really, measured it at that level of precision. But this is what they claimed. So this is what we're going with. This is what they gave us. All right. Anybody have any other questions or anything about these? We're going to move on to that information about deciding uncertainties. Okay. So I took that really super long document that was like 50 pages long and I extracted the parts that we care about. So this should be a little easier to see compared to what we were looking at last time with these examples. All right, so we have a meter stick with a pen. And we're measuring the length of the pen with the meter stick. And we have some zoomed in images here so we can really see the edges of the pen. The 16 is our 0 point. We have lined up that end of the pen perfectly on the 0, we're going to assume. And then we have the top or whatever right-hand side of the pen at 30 point something centimeters. So we're going to follow the algorithm, I guess you could call it, for determining an uncertainty when using a tick mark device. I had analog device here before, but that might be confusing. Like I'm talking about electronics. So I'm just going to say tick mark device. You have tick marks on a ruler, on a meter stick, on a pan balance, on a micrometer caliper, on a metric dial that's like, turning in an angular way. All those still have tick marks, and you still use this method for determining uncertainty in those cases. If you don't remember how to use a micrometer dial or anything like that, if you have, if you can't remember how significant figures work and things like that from introductory lab, go back to this main big document. It's all there. Just FYI. Okay, so step 1 is determine the smallest increment. We can see that each centimeter is divided into 10 increments with the tick marks. So the smallest increment is 0.1 centimeters, a tenth of a centimeter. And based on the length from 16 to 30, I can measure a distance of 21.4 centimeters from these tick marks and kind of guesstimate a 21.42. An extra, I can try to like guesstimate how far in the tick mark is it. I guesstimated or like used my eyes to see that it was about 2/10 or maybe 1/5 of the way across a tick mark when I was doing this. Okay, so that was what I measured for the value of the length of the pen. And then I decided on the uncertainty. I tried to take that the segment in between the tick marks and divide it into some number of smaller segments. So I chose n equals 4 and was able to kind of come up with some basically come up with like the smallest possible value I can observe is that 0.025 centimeters with my eyes. I'm going to round that up because I don't round down ever, and I have to have one significant figure. So I take that 0.025 centimeters, I take the smallest increment. I think I can divide it into 4 based on my viewing. I end up with 0.025 centimeters for like the most I can judge on one side or the other of the endpoint of my pen. And I round that up to 0.3. So I end up with a final uncertainty of 21.42 centimeters plus or minus 0.03 centimeters. So there was definitely some decision making there. I decided what N was going to be, capital N. Maybe you would decide 2. Maybe you'd be more comfortable with 2. Maybe you'd be more comfortable with 5. Maybe you have really like awesome eyesight, or maybe your eyesight sucks, or you don't have a tool to, if you have like a lens, like a magnifying glass, maybe that you could make N bigger, So it depends on your situation and your personal level of comfort when you're deciding uncertainties. Any questions about that or comments, feedback? Okay. What about a digital readout? Remember this? The SPY motion detector from 1150 or 1151. It had a digital readout. And so there are certain conventions for measuring a digital readout. There's less decision making. There's not like this tick mark with some number of, made up sub tick marks that you're going to have to come up with. It's a little bit more straightforward. But you do have to figure out, is this fluctuating or not? Sometimes you'll be, using a voltmeter that has a changing value. Or you're sometimes using even a tick mark scale that has a needle. If it's fluctuating around certain values, you're going to use these same sets of rules. So if we have non-fluctuating digital readings, that's easier. Here's the example that we're going to go through. Let's say you're on a digital bathroom scale and it says you weigh 145.3 pounds and it's not fluctuating. You might actually weigh 145.26 pounds or 145.31 pounds or 145.34 pounds. We don't know which of those. And there's lots of other values in between that it could be. We just know that there's that 0.3 there, which might be, you know, not exactly 0.3. It might be like rounded down or rounded up. So the minimum uncertainty is going to be dictated by that precision of that scale, and it's going to be plus or minus 0.1 pounds, because that is the digit of highest precision, and we assume that the uncertainty is the smallest reading in that digit of precision. Okay, so let's say the scale read 145 pounds, 0.0 pounds. That means you might actually weigh 144.9 pounds, or you might weigh 145.1 pounds, or you might weigh 145.0 pounds. But with your uncertainty of plus or minus 0.1, you have to give a range. You have to report your final value as a range, 145.0 pounds plus or minus 0.1 pounds. Okay, pretty straightforward. I don't think there's any surprises there. If it is fluctuating, there's a few more steps you need to take. Oops, sorry. I need to scroll down here. Okay, if it's fluctuating, then, like for example, let's say you are on the scale and it is fluctuating between 145.1 pounds and 145.4 pounds. So it's showing all these different values in between in that range. So what is your reported value going to be? The weight could now be anywhere between 145.0 pounds or 145.5, according to our old uncertainty. That's the range that this could be in. So what do we report? What we're going to do is take the mean of that fluctuation, and that's going to be kind of like part of our uncertainty now. How far is it going back and forth? That's going to determine basically our range of uncertainty. So we take the mean, we take the max value, 145.4, we add 145.1, we divide by 2, we get 145.25. That's our mean of the fluctuating range. Now we're going to find that uncertainty. We're going to take the max value minus the min value of the range and divide by 2. Okay, so that's half the range. And we're going to add that to the original minimum uncertainty. We take the original uncertainty, we add this new uncertainty from the fluctuation. So my reported value is the average value inside the range, and my uncertainty is the old uncertainty plus half the range of the fluctuation. So we take 145.4 minus 145.1 and divide by 2 and add that old one. We get 0.25 pounds. We need that to be one digit, so we round up to 0.3. And then our final reported value is 145.3 pounds plus or minus 0.3 pounds. Because we had to round this up to 0.3 as well and make the digits match. Any questions about that? Okay. All right. If there's no questions, it's breakout room time. So here we go. I'm going to stop sharing and I'm going to open up. I think we have 5. I can't remember if there's 6 or not, whatever. All right, so there's 6 breakout rooms. I have opened them. Oh, I guess it kept your old assignments. Okay, well, that's nice. There's your rooms. I'm going to send a file for the question that I'm asking you.
Also, last time I was assigned to the room that wasn't on the list, so I don't know. I mean, I could just join the same room that I was in before, but last time.
Yeah, I'll put up the list, so if you're in the wrong room, you can get into the correct one. Thank
Okay.
you.
Dr. Hester.
Yeah.
I think it was put in the wrong breakout. Oh, wait, I can join it. No, I think it was put in the wrong breakout room.
Okay. I'm gonna put in the text which one to join. Did you just get those questions in the text?
Yeah.
Yeah.
Okay, and I'm broadcasting those. All right, I'm putting the breakout rooms here. Yes, there are 6.
Okay,
Hey, Dr.
What
Hester.
the hell did I just do?
the
So,
message disappeared before we could read it.
Did
Yeah,
I just join a breakout room? How did I even do
yeah,
that?
And Sam invited you.
I
Oh,
invited you in here.
Oh.
The message that you just sent out, when you send it to everybody, when people are in breakout rooms, it appears as a little banner at the top of the screen, but it has a limited number of characters, so we couldn't scroll and read everything, and it goes away
Oh.
after.
Yeah, so we weren't able to read all of it.
Okay. You weren't able to read all of the questions?
Yeah.
No, we weren't.
All right, I will put them in one at a time.
Okay.
But how do I get, oh, okay, now I'm gonna leave the room. I'll put them in one at a time. Let me know if it doesn't work.
Okay.
Yeah, I think we might have to. Did you see that?
Dr. Esther. Yeah, we're confused.
Yeah.
I don't mind staying in the breakout room that I'm in. If it's
I think this is the breakout room now. It has
the
become.
one I was in previous. But I don't know.
Oh, there we go. She posted a list.
Yeah,
Oh.
but now how do you get to your breakout
Oh.
room?
Yeah.
The problem is we can't pick the breakout room.
You if you have an old version of Zoom, it's something they've put in somewhat recently. You have to update it. It's annoying.
Oh, that is annoying because, oh man.
How do you
Kind of
update
ruined everything.
Yeah. It won't even let me look at breakout rooms anymore. That's not even an option for me.
Yeah, same.
Dr. Hester, I think you're muted. I don't know if you meant to be muted.
Okay, you know what? We're just gonna go through these examples. That's what we're gonna do. I'm gonna have to reinstall Zoom, I guess, so it gets rid of the old breakout room assignments. All right. Did anybody get to like actually thinking about a question? No. Okay.
I mean, we got to the first question about the 0.366 constant volts.
Okay. So did you have a like response written down you can show us?
Poorly, but yes.
Okay. Let's see.
If you can see that. Oh, I think it's backwards.
No, we can. It's not backwards for us.
Can you see it?
Yeah, 0.366 plus or minus 0.001 volts.
Yeah.
Let's see if that's what. Yeah, that's correct. What the hell was I writing? That was really late at night. I'm sorry. Tristan's answer was correct, everyone. I will fix this document. And it's not uploaded yet to the website anyway. Okay, so yeah, that was correct, Tristan. What about the next question? Did anybody get to the next question that I am displaying here on my screen? A digital multimeter is reading a voltage that fluctuates between 0.363 and 0.365. What do we report that final measurement as? So we follow the algorithm we just learned a little while ago. We take the mean of the minimum and maximum of the readings, and that's going to be our reported value, 0.364. Then we take half the range of the fluctuation, 0.365 minus 0.363 divided by 2, and add that to the minimum uncertainty implied by the given values, which would be 0.001 volts. That would be the uncertainty if it wasn't fluctuating. Okay, so we do this math and we get 0.002 volts here for our fluctuating situation uncertainty. And so our reported measurement is going to be 0.364 plus or minus 0.002 volts. What do y'all think? Make sense? Okay.
Well, in number 2, wouldn't you do 0.366 minus 0.362 because you have to account for the uncertainties in your initial measurements?
I didn't hear you. Say that again.
So for step 2, wouldn't you use the value 0.366 and 0.362 because you have to account for the uncertainty in your initial measurements?
Okay, let's go back to the example and see what they did here.
I might be wrong. I might just be.
It's okay to do that. I'm not saying that would be wrong. I think that's Henry talking.
Yeah.
I'm not saying that would be wrong. That's a little bit more safe actually than what this, kind of like conventional way of doing it is. Since it could be between 145.0 and 145.5, you can use that as your like range that you're going to determine your uncertainty with. But it's also okay to do it this way. This is the convention. So I would say either way is correct, Henry. Just a little bit more safe, a little bit more honest. Okay, I think there's a couple more here. The known length of a string is 60 meters. And you measure its length to be 56.5 centimeters. Did I say 60 centimeters? 60 centimeters. You measure its length to be 56.5 centimeters plus or minus 0.1 centimeters. Is this high or low precision? We didn't talk about this section yet, but we have talked about it a little bit.
What are you measuring it with?
A meter stick. But just from looking at this number here, is that high or low precision is the question. What we do to answer that is consider the percent uncertainty. So I take the uncertainty, I divide by the value, and I get 1.7%. So 1.7% is pretty small. So I would say that is high precision for that measurement, for that length of that string.
Really, when it comes to like what I would say is when it comes to precision, like whether it's high or low, that would depend on what the application is for. Like,
yeah, it's definitely a decision-making situation, and there's like a range of what's high and what's low, and what's like, I'm not sure. I tried to do examples that were like obviously one or the other. But I agree with you, Ethan. That is definitely going to depend on the situation. So you've seen this image before that demonstrates high accuracy and high precision in a picture form. I put some examples here of determining if these reported values have high or low precision, and do they have high or low accuracy. So let's go through this example first. Okay, let's consider some researcher is collecting gravitational acceleration data. apparently in one small space where the acceleration is known to be 9.83 meters per second squared in that region. That's the like known accepted value. We need to figure out if each of these measurements has high or low precision and high or low accuracy. Okay, so the first one is 9.83 plus or minus 0.01 meters per second squared. Is that high or low precision? Is that high or low accuracy is the question. Okay, so what we do to find out if it's high or low precision is check that percent uncertainty. We take the value 0.01, we divide by 9.83. We get 0.0001, which is 0.1%. That's small. 0.1%, we can pretty much all agree is small. So that's a very high precision measurement. Is that an accurate measurement? It might be really precise and total crap. Is it accurate? Is it correct? In order to determine if it's correct, we find the percent error. We take the known value, we subtract the measured value, we divide by the known value, that's 0. It's pretty small. So that's a very high accuracy in this case. What if we instead measure 9.8 plus or minus 0.9 meters per second squared? Let's say that's the measured value and the uncertainty for whatever reasons. That's the reported value. To find if that's a high precision or low precision situation, we look at that percent uncertainty. 0.9 divided by 9.8 is 0.09 is 9%. 9% is not really satisfactory for most scientists. That's pretty big. So that's a pretty large uncertainty, which is going to give us a low precision. But again, like Ethan was saying, it depends on the field you're working in. In optical tweezers, 9% error is pretty damn good, for example, like in my field. So depends. But if you're measuring the speed of light in senior seminar, most people get like below 1% error or uncertainty as well in that class. So that's a pretty, you're usually doing things with pretty high precision in senior seminar and in the classes, other classes where you do measurements. All right, is that a large percent error or not? Is that an accurate measurement or not? We find the percent error. It's 9.83 minus 9.8 divided by 9.83. That's 0.03, which is 3%, which is relatively low, which is going to give us a high accuracy. A low percent error means high accuracy. What about 12.64 plus or minus 0.01? This is obviously not close to gravitational acceleration. Although it is nice and precise. If we calculate that percent uncertainty, we get 0.08%. So that's really small. So that's a highly precise measurement and very, very wrong. The percent error is 28%. So that is a high precision, low accuracy measurement because it's very far off from the correct value of gravitational acceleration, but with a tiny uncertainty. And then the last example here is where we have low precision and low accuracy. The value is pretty far off from 9.8 meters per second squared, and the uncertainty is pretty large compared to the measurement. So we have a 7% uncertainty, which I would, again, it's like, do you consider that large or not? I think yes in this case. And then 28% error is definitely quite large. So we have low precision and low accuracy for that. Okay, so one more example that I'm going to ask you all to think about. They're on the screen. The known length of a tube is 6 millimeters long. You measure its length to be 6 millimeters plus or minus 1 millimeter. Is that high or low precision? And is that high or low accuracy? So first, is it high or low precision? Anybody?
I would say that it's a low precision because the measurement itself is 6 millimeters, whereas the difference is 1 millimeter, where that's higher. So I'd say the precision is pretty bad with that.
Yeah, it's 17%. That's terrible. That's really high. 17% of the measurement is uncertainty. Not good. So that's not a small uncertainty. So you have a low precision here for this measurement. Correct. Okay, what about accuracy? Duh. 6 minus 6 is 0. So it is highly accurate, but just not very precise in this case. Okay. Any questions? Anybody about any of that? Okay. We still have a few minutes left, so I'm going to keep talking. I'm not going to try to put you in breakout rooms again today. I will do my best to make that work next time. Sorry it hasn't worked today. I do want to talk to you about graphing, plots, making plots. That's our next topic. And we are going to look at an example of a plot, and I'm going to ask you what is wrong with that plot. Because I think you might already know a little bit about plotting. Okay, so tell me, I'm going to share my screen. Tell me, what are all the things wrong with this graph here? Just shout them out as you see them. What's wrong with this graph?
They're not axes unlabeled.
Axes are unlabeled, yes. What else?
Zero's not at the bottom for the y-axis.
Zero's not at the bottom.
There's no units.
There's no units.
There's no
These points
title.
should not be connected like that. Or at all, actually.
Say that again?
The points shouldn't be connected like that.
That's right. The points should not be connected. Yes. What else?
There's no title. Like, what is this even a graph of?
We have no idea what this is. There's no title. There's no tick marks either. I don't see any tick marks.
Yeah, there's no grid, so we don't know where's every point.
No grid.
It looks ugly.
It looks ugly. Okay, good job. That's a lot of things that we just found. So let's go through with the last couple of minutes here and look at what are some things that we need to remember when we have a good graph. So that was several of them. We're going to cover them all in this slide, this next couple of slides. And there's just some things to know, like you can show off with your knowledge of knowing that the horizontal axis is called the abscissa. And the vertical axis is called the ordinate. So if you want to sound fancy when you're giving a talk, you can you can say abscissa instead of x-axis. All right, we also should have a title for that graph, like Tristan said, unless it's in a paper. If it's in a paper, that information goes in the caption under the figure. Journals don't let you put titles. All right. By the way, this is an example of a nice graph, a correct graph here on the slide that we're looking at. The title of your graph should be clear and uniquely identify it. I should be able to understand what this graph is by looking at the title or the figure caption. I should completely understand it, assuming I know what a flux rate is and a crucible is. We put the independent variable on the abscissa, as you know, on the x-axis. We put the dependent variable on the ordinate, on the y-axis, and that scale should be easy to read. Real quick, I'll go through a few more. The zeros don't actually need to be there, but we should have an axis indicating what value we do have at the intercepts. That's one thing missing here. The data should fill up the space well. It shouldn't be concentrated in a corner. The tick marks should be there and they should be helpful. It'd be nice to have minor and major if you can fit them. The axis labels need to be words or phrases, and then you should also have units there. Even if it's an arbitrary unit, you say arbitrary unit. We use small symbols for our data points, not huge ones. And they should be unique in shape and color if we have more than one data set. And lastly, and very, very importantly, we must include the equation for the fit if it is a fit. This is indeed a fit on this graph. We have included the equation for the fit. It is not y equals mx plus b. It is flux rate equals a slope times the distance from the crucible plus the y-intercept plus or minus that uncertainty for the slope and for the y-intercept. So all those should be included with proper units and symbols. And I'll stop now. Thank you so much for waiting for me to finish that. Do we have questions or comments? No one. Okay. All right, I'm going to give you some really crappy graphs next time, and you're going to have to figure out what's wrong with them. Hopefully in breakout rooms, if I can figure out technology. How many physicists does it take to figure out breakout rooms? Thank you very much, and I'll see you next week.
Have a good day, Dr. Hester.
You too.
Good day.
Thanks. Bye.